Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Ivan Ostojic, partner at McKinsey Company. Ivan and I talk about what success looks like and how to avoid failure in quantum computing proof of concept projects. We also discussed how we know whether 1,000 qubits will be a quantum computing panacea, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Ivan, and thanks for joining me today.
Hello, Yuval. It's a pleasure to be with you.
So who are you and what do you do?
Who am I? There are many facets to that question, but let's focus on the professional part. So I'm Ivan. I'm partner in McKinsey, and I actually hold a great passion for technology-led innovation. So we have something within McKinsey that we call Global Technology Council. It's like a think tank where we gather people that are external to McKinsey and some that are internal, and we think about future of technologies. And there is 70 people there. So I lead that part operationally, and we have some deep dive groups. One group is so there is an overall group that is looking at tech trends and how are they changing faces of the industries, and then there are some deep dives that are looking in particular technologies, and one is dealing with machine learning ops, and the other one is looking at quantum computing. So I lead all the quantum activities within McKinsey within that emerging technology group, and then also I lead our innovation practice in Europe, Middle East, and Africa, and as well like a large part of business building practice. So that's a bit more than what you want to know, but actually it's interesting because these technologies will either find its way, like quantum will either find its way as transforming the core business or by companies building new ventures. So that's why I mentioned it. And by training, I have kind of a dual background. I work a lot with tech companies, and they often talk about horizontal, vertical. So it's a little bit like me. I have a PhD in life science, so that's my industry vertical that I know the most, although I serve clients in other industries, but also horizontally, I actually have a master's in technology management and innovation from ETH in Zurich. So I combine those passions also in my work. And quantum, I've been spending now more than 3 years looking. I think it's so disruptive, and it holds great promise that we can solve some big problems. So I'm very passionate about it, and we have a large group within McKinsey. Maybe, number in when we started digging, there were kind of tens and tens of people who have a PhD in quantum. So we are. I got a group of friends that is working with me there that has a very deep technical competencies.
Excellent. And do you work primarily with European clients or global clients?
I work globally. But typically it's like, given that this is a cutting edge technology, is the most, at least my own activities, some parts of the Far East, Europe, and then United States, and what are the hubs, and Israel as well. But that's kind of, we counted as Europe, also in our division.
You mentioned technology-driven innovation. Do you see quantum as a standalone activity where companies are just engaged in quantum projects, or do you see it as part of a bigger innovation strategy or growth strategy for a company?
So I think it's a great question. It depends sort of who you are, right? So if you're a tech company, it can be like a standalone product in sort of a business to business terms. So like either manufacturers or hardware or cloud service providers or cloud service plus consulting and so forth. I think if you're an enterprise, it's rather going to fit somewhere within your business. So it could be like a business model transformation. Let me just take you through kind of semi-made up example, but relatively realistic. If you're a lubricant company today that produces all kind of lubricants, today this is done implicitly by people kind of trying, and they have a lot of experience. I think, with quantum, it holds a promise that it could kind of simulate the optimal mix. So you could create like a platform company that just literally simulates that part of the chemical process, and there is some lab automation that produce that. and goes into the value chain. So it's still within the core business. It's a bit of a different business model, I could imagine, but it could be like a new venture. And then there are companies where, or industries where this will be deeply entrenched within their current business model, and it will dramatically or less dramatically, but significantly improve. So take banking, we all read, who are in this quantum field, around recent research with, optimizing portfolios. I mean, that's core what banks do. And, if you can improve something few percentage points, it's a huge generation. So they will need to master that activity. Similar, it's within pharmaceuticals or others, where this is kind of part of the core of what they do. And then there will be some potential for improvement of operations. I mean, we also read about the use cases like scheduling or logistical optimization. So it's going to depend in which industry you are and where in the your value generation chain will hit you. And to summarize, for many enterprises, it will go through their core business. For some, this would be either variants of their current business, but more kind of platform driven, or actually genuine new value creation. Think about sustainability and carbon capture, the fact that we might be able to simulate some of the molecules. I mean, when we have a right quantum hardware, not today, that's genuine new businesses. And so that's kind of a bit how to think about it. Now we would need to cross different industries versus where the value is being created and then decide what's the optimal path.
A lot of companies today are experimenting with quantum. Sometimes it comes from the top, sometimes it comes from engineers or scientists who are just interested in starting to do it in their off time. But what does success look like today with a quantum project? Is it just proving that you could do something with quantum that you did with classical? Is it truly a unique advantage? I mean, what does success look like in a quantum project in your eyes today?
Yeah, so I mean, to be quite frank, I spent a lot of time and that, we want to kind of understand this technology much ahead of the curve. And we try to map the use cases that companies were experimenting with and so forth. And so far, it was relatively difficult to find the use case where, genuinely quantum hardware. So I'm not talking about quantum inspired. What we create can beat or outperform, any kind of classical algorithm. And I mean, Yuval, I follow your publication. A lot of, and your audience, error correction, etc. So simply, hardware is not ready today to produce something that would have superiority in terms of business impact. Maybe there are a few use cases, but jury's still out there, whether we benchmark. But I think just not to overhype where we are. So given where we are and being realistic on the roadmap of the quantum development, I think the biggest success would be few. Number one, understanding whether quantum has a potential to be completely disruptive to your industry, something like implicit industries where a lot is driven by science. And now we can simulate things like in chemistry, or actually it will be enhancement of what you do today. And then understanding, okay, what are kind of most promising use cases and getting your heads dirty. I mean, there was a good example of Airbus challenge and Volkswagen has a challenge. I'm pretty convinced, although I didn't speak directly with these companies, that they're not going into it expecting like big dollars, but they do want to see where is the technology frontier. What can we learn? And, what can we actually, at least, on the research level, produce sufficiently realistic algorithms to prove that, this case will be feasible if the hardware works. So I think with those three, I would say those would be my kind of areas to answer your question directly. First, understanding where in my value chain it will hit or create opportunity and how. Number two, learning with these experiments, where is the frontier? And number three, maybe in the research area, kind of proving that some of these algorithms could at least, sort of forward-looking theoretically help. I think that's what's realistic to expect, given where the hardware is. And then some offshoot, I spoke to many companies, was that then they produced like quantum-inspired algorithms that were doing useful thing, and they were quite happy. And I think if you come in with appropriate expectations, I think you can actually manage your business stakeholders and not overhype the technology and actually drive this steady growth that we are witnessing now.
So given that that's your definition of success, it sounds like failure would be just setting expectations that are too high, going to the CTO and saying, give us $200,000 and we're going to revolutionize the way we do TSP problems or anything like that. And then, of course, because the hardware is not quite there yet, failing relative to these very high expectations. Is that correct?
Yeah, I would say yes, overhyping and promising kind of unrealistic results within a year or two, in a way. I think that would be really something that would be not successful. I think having a strategy though would be very good, because some of the hardware players are essentially more or less confident, but there is a probability that they will have hardware rather earlier than later. And if there's going to be a limited capacity, it's also a question, how do we almost get engaged now in the project to have like a first seat in the row? And for that, you need a strategy. Do you need a first seat in the row or not? Because if you're going to be disrupted, you rather are there early. If this is enhancement of your business, you have a little bit of a privilege to wait. So that kind of is important. I think the case you described is probably absolute like disaster, because you know how these corporates work, the metabolism. You go there, something promise, they do something, they tick the box, it didn't work, and next time somebody is coming with a good idea, maybe technology is more ready, people will say, oh, we tried this, it didn't work, and that memory somehow of failures in many corporations, I witness it pertains during time. So I think that's something we should avoid. We should just responsibly position where the technology is, but also what's the promise, and then kind of build a strategy. How do we experience it without setting expectations too high, in a sense of you will get something here and now?
On the hardware side, a good approximation to the strength of the hardware is the number of qubits, because people say, oh, I'll have 100 qubits next year and I'll have 1,000 qubits the year after, and a certain number of qubits I can do error correction and I can do this, that, or the other. But obviously no one can simulate what a 1,000 qubit computer is going to look like or is going to be able to do, because that's beyond the capabilities of classical computers. How do we know? How do you know? How do others know that a 1,000 qubit computer is really going to be breakthrough in terms of the algorithmic abilities and the business value that it delivers?
So I think that's a great question. So far, what I've kind of seen is actually quite a good research from either smaller companies or actually large tech giants, where they focus on a particular problem, let's say some chemistry simulation problem, and they really go in depth, mathematically and so forth, explain why quantum computers could solve this, and then give some parameters. I mean, there were even some very fundamental papers that are 100 pages long and go into very much detail. So I think there is no way to know until we put the whole thing together. But I think this theory and what we know from the theory and how the different hardware work and the equations that went into there could give us confidence. So it's all about de-risking. It's not about being 100% certain. Could give us reasonable confidence that we can de-risk, that there is a probability that if hardware work as intended, meaning no faults and so forth, that the algorithm will work. But I think that's the best we can promise. It's the levels of de-risking. It reminds me a little bit to pharmaceutical industry. When you're putting a new drug, in the phase 1, there is like a 90% probability that it will not work. And then as you cross certain stages, the probabilities get updated, and hence our expectations and valuations and everything else. And this kind of, on a very abstract level, also reminds me. So at the moment we have a theory, and it should kind of work. Then we do a little thing in a simulator. We get some, as you said, it's not easy to simulate 1,000 or more qubits, but okay, these results give us next level of confidence. And then there's next level of confidence. So where are we on this de-risking path? It's sort of what gives us confidence that this could work, but it's not like 100% guaranteed, as you say. I mean, we won't know until we put everything together.
When I speak with companies about what they worry about what they would like to see. So usually three things come up. One is stronger hardware. Okay, we need 1,000 qubits or 100 qubits or whatever number they need. The second is people. We need more trained, qualified people that understand quantum information science, that can create algorithms and so on. And the third thing is the software development platforms. How do I create software for a 1,000 qubit computer? I'm no longer going to be able to manually connect the gates to the qubits and so on. So I have a two-part question there. First, do you agree? Maybe there's a fourth or fifth one that you think is missing. And the second part, do companies really worry about the software part, or is it just our wishful thinking at Classiq that that's the case?
No, I think, I mean, you know, when you say companies, it's, I mean, there are really few companies that move at scale that they think really, let's say, quantum transformation as they would think, let's say, artificial intelligence, but there are groups within the companies that are thinking about this. And we spoke about it. And so I think there is one more point I would add, which is causing, let's say, a lot of confusion or so in many companies, and that's more or less, I call it strategy, but it's much more than a high-level strategy. It's actually which use cases, you know, what's my are where I should start experimenting and so forth. Some get lost really there in a way, you know, where on the value chain this has opportunity and so forth. And what is other is, I mean, to devise that. And I recently gave one interview. You know, you need something like, we called it in artificial intelligence, we call it like business translators. So you need people who understand quantum theory of quantum computing sufficiently enough to understand where is this applicable, but then at the same time have sufficient understanding of business to know what business problems they are. And this part is a little bit difficult because, you know, you would need to kind of order cases across your value chain. Let's take pharma. Is it chemistry? Is it imputing missing data based on expectations from the hardware and so forth? So that's just, I would add that part on the use case roadmap and so forth. Now, I completely agree with you. People, we don't have enough, and the gap will become probably even bigger. I would agree hardware with some nuance, right? Because I mean, in our tech council, we have representations from very different companies that have different approaches and so forth. There is constant debate, can we do something within NISC or not? And some people say, forget about it, nothing useful will come. The others, you know, say, yeah, we will be able to error correct with software and we will be able to produce something beneficial. And I don't want to be a judge of that. It's a debate, as you're aware, but I think, you know, whether companies want, you know, 1,000 qubits or more, that's a question. I mean, I think they want a useful hard quantum computer where they can kind of deliver the business problem. Just a bit of nuance there. And then I agree with you with software, because I think even in our predictions, and this happened a few years ago, now you see this kind of in practice, many of the business problem will be solved in some sort of a hybrid sequence. So, you know, I have, let's say, sort of optimization problem. I can solve 70% of equations on using high performance computer. And then I need some part on quantum computer in order to get coefficient or something like, you know, having somebody who can understand what A needs to be done, translate it into actually lower level of kind of equations and so forth, and then translate it into software workflow that will produce that at scale. I think that's quite actually critical. And I think, you know, we didn't see also, we can learn from artificial intelligence. You know, when you had a bunch of data scientists doing sort of, you know, some AI experiments, everybody was impressed, kind of, wow, cool, you can do this, but there was no like business impact. And the reason why there was no business impact is because this was not productionized for people at the front lines to use it at scale. So now you have all this wave of development, machine learning operations, which are really, and I think we can learn from that. I think we can kind of preload that period in quantum. Yes, we need experiments, but I think we will need software learning from this to be able to scale that at industrial grade. So for these two reasons, because my prediction will that workflows will be complex and it'll kind of call different libraries and so forth. You need binding tissue of that, which is software. And the second, it's not, all I'm trying to say is not like, oh, let's throw a little bit of data and do something in R. No, it's going to be more complex. And then the second is, you know, ability to scale gets much more powerful with software. So that's why I think these 3 or 4 components: use case roadmap, when do we do what, when, with appropriately managed expectations, people, hardware, useful hardware, whether it's stronger, but definitely useful. And then the third one is the software. I think those are probably the most critical elements.
So you mentioned quantum ops, or the equivalent of machine learning ops or AI ops. Do you worry that quantum computers on the cloud, you need to have an SLA, you need to have good response time, you need to have reliability, or you're saying, no, the Amazon and Googles and IBMs of the world will figure it out because they've done it so many times in the classical world?
Yeah, I think, I think here's kind of, if I may say something a little bit provocative. So I think they will figure it out. But for me, this question on the tech side, what really is the business model? It's also not 100% resolved. And the question is, who's the first to get to market? And here's what I mean. In certain areas, quantum computing will generate so much more disproportionate value. Take something like sustainability or so. You're literally creating new markets by simulating, let's say, molecules that don't exist today. The question is, do companies want to sell capacity for that, or they would want to participate in the value that's being created? And, are we going to have abundant capacity? Because if we have abundant capacity, it's pretty obvious. It's going to go into a cloud, and people are going to, many companies will hook on the cloud, have their workflows. And I believe these companies will figure out, how to do it. Because many of the applications, unless kind of real-time optimization of logistics and supply chain, there was an accident and I need in a second. Actually, quantum would probably be more powerful than standard, but for that I need the response time that's very fast. Others, you can still live a bit with, like if you need a couple of days to do a simulation and so forth. So that's one. But I'm just going back to my train of thought. So if we have an abundance capacity, I think they will figure out and things will go to the cloud. If we don't have abundant capacity and we are generating extremely high value in certain industry verticals, we might not even see many of these like quantum computers, at least in the first era, let's say first 5 years or so, being exposed very broadly into a cloud, if you see what I'm trying to say. So, or maybe there'll be a third option where you have a vertical and a horizontal kind of a hybrid strategy. So there'll be certain vertical solution for certain industry and then a cloud for everyone else. That could also be. But I'm not so worried that they won't solve like a, I think the more thing is, by the way, just sorry, I'm a bit kind of speaking as I'm thinking, but there is one thing though that is important. So we analyzed one of the quantum use cases and we realized actually there might have been an uplift in some optimization thing, but actually there was a lot of loss on the information transfer because it was done in a hybrid sequence between quantum and then a cloud and so forth. So what I'm more worried is this quantum information transfer, because to exploit the full power, we'll need certain information to be exchanged in a certain way. And that's another technical bottleneck, let's call it like that it's fast enough so that you ripe, the full benefits of quantum.
As we get closer to the end of our discussion today, some companies look at quantum as, we're going to be generating this completely new product or type of service or platform, as you described, that was not there before. And others say, I'm spending X amount of dollars on high performance computing, and maybe with quantum, I'll be able to spend 30% less and get similar results. If you were a betting person, which one do you think will be more prevalent, the new product or the cost saving side?
I think so. I think the cost saving, as you described, I would bet for the new product. You see what I mean? So the way you're describing is like less spend on infrastructure cost in a way, because I'm spending so much on AI now, I can do it faster. I'm not sure if that's the consideration. I think the cost in a sense of, I have this supply chain and now I can cut 20% more cost because I have a better scheduling algorithm. That might be for a lot of industries. And we'll publish now one report where we analyze very detailed use cases. That might be for some industries. I still kind of think there is a lot of opportunity, if you ask me, in this upside, because a lot of applications are like, small, what do they call, small data, big compute. And I'm referring back to chemistry, molecular simulations, and so forth. And there inevitably you come more to really opening new areas of application. So if I'm a betting person, I'm betting in number one.
Excellent. So Ivan, how can people get in touch with you to learn more about your work?
So I think the best is if the people contact me via email. I mean, I'm happy to share. I don't know what's the appropriate way. There is a lot of now reports coming from our side where we are trying to analyze. It's difficult to analyze something that's coming a few years down the road, but or number of years down the road. But we are trying to analyze impact on different industries and publications. And on many of these, I'm co-author. So that's the other way to find it. McKinsey, like Game Plan for Quantum Computing, was our intro publication. It was high level, but was just supposed to put the basics for executives that read that. That could be the other way. And my email address is my first name, which is Ivan _ my last name. It's Ostojic @mckinsey.com.
Very good. Ivan, thank you so much for joining me today.
I hope it was interesting. Thank you, Yuval, for having me. I enjoyed the conversation with you.